This is a short video to show how optimization works, Chapter 7. Not intended to be complete, just to give you something to refer to just see how you set up an optimization. The example I'm going to use is from Chapters 1 and 2, the peak load pricing problem, in particular Chapter 2's problem, where we had uncertainty, an uncertain multiplier each hour of the day. It could be a sense of variation, standard deviation of 25% higher or lower in each given hour. And we compared pricing $50 right here all day long, every hour, versus the peak load pricing $75 during peak hours, $25 during off-peak hours. And if you recall, when we had no uncertainty, you lose $7,000 if you use this constant price all day, whereas you make $16,000 if you have the time varying price, the peak load price. With uncertainty, it turned out that the profit difference was a little bit larger. It came out to $28,000, just over that. The probability was 100% that you would have higher profits with peak load pricing. So to turn this into an optimization problem, we can go back and realize that, in fact, these two prices were just given to you, 75 and 25, and under these circumstances, are those the best prices or could we do better? So that's an optimization problem. I will say you can explore and get good insight by just building some data tables and varying these prices and sort of seeing how the profits change with different sets of prices. That's what optimization is doing, except it's going to do it more completely and actually come up with solutions. So go into Risk Optimizer to Model Definition. We have to tell it what the goal is. We're going to try to maximize our total profits with the peak load pricing. So the cell we're interested in is right here, profits with peak load pricing. And because there's uncertainty, you can choose to various things to optimize, maximize the mean. You could decide to maximize a certain percentile, the 90th percentile of this, or the median, or minimum or maximum standard deviation. So you have a lot of choices. Let's just try to maximize the mean. And the things we can adjust are the prices. So let's go and add a decision variable for our peak load price. And I'm going to let it vary in the range of, let's say, 50 to 100. And if you want an actual precise solution, you will want to let it be continuous and vary with any value in that range. But Risk Optimizer will work a lot better if you proceed in steps, with the steps being discrete step sizes and fairly large ones at first. Let's go with steps of 5. And then because right now I have no idea what the solution looks like. In fact, I'm saying 50 to 100, it could be 0 to 100, it could be 0 to 1,000. I mean, who knows? You don't have to set a huge range, because after we run it, if the solution comes out near one of these extreme values, if it comes out at 50 or at 100, then I need to go back and enlarge the range, because if 50 gave us the best and I didn't let it go below 50, I should try a value lower than 50. I'm just taking a hunch that maybe it's somewhere between 50 and 100, but I really don't know, but we'll run it and see. And in fact, suppose the solution does come out somewhere between 50 and 100. I'm only allowing it to vary in steps of 5. Once we see that the solution is, let's say, somewhere around 70 or 75, we might narrow the range to 60 to 80 and go in steps of 1. And then eventually, if you needed a real accurate solution, this was your business, so every dollar mattered, what you would do is set it on any and probably run it overnight, because it would take a long time to, if you give it an infinite range of values, it could take a long time to find a solution. But I find Risk Optimizer works best if you don't try to solve the problem in one fell swoop. You do it sort of iteratively, where if you don't have an idea what the range should be, set a pretty wide range with big steps and then start narrowing it down. So that's our peak load price. Our off-peak load price is this one. And I'm just going to set that to range from 0 to 50 with discrete steps of 5. You can add constraints. A simple kind of constraint might be that the prices have to be greater than 0, but that's automatically taken care of in a sense up here by restricting the range to only be positive, so we're not allowing it to be negative. If it's a portfolio problem, you probably want a constraint that the total amount of money that you allocate to different assets doesn't exceed the budget that you've got. So sometimes constraints need to be put in. Often constraints are handled by the way you set up the problem to begin with. It may be in the model that you have constraints. So for instance, we could constrain that demand not become negative, but that was already built into this model. If you remember, we specified that demand could not be negative. I'll show you that here in a second. So we don't need any constraints here. They're none that are necessary. Let's go ahead and just enter that. You'll notice with demand, I use that maximum so that it could never go below 0. So it's in the model. We don't have to constrain that demand not be negative because it's already taken care of in the model. So that's a very simple setup. We're going to optimize one cell. We have 2 decision cells that we can vary. If you go to the settings, you can limit how many different values it will try, or you can limit the time. Let's go ahead and limit to 5 minutes. It's not going to take 5 minutes. It only has roughly 10 values to try for each of the decision variables, so it's going to be very fast. That's also the advantage of approaching this iteratively, is that it can proceed quite quickly. So I'll set that at 5 minutes, and what it's going to do is it's going to try all those different values that we asked it to try for the decision variables. But each time, every set of values, it's going to run another simulation and then look at the mean of the profits from running those simulations. It's probably a good idea to lower the iterations like to 1,000, because otherwise it's going to run, even with only a few values to try, it's going to run very slowly. Every set of values, it would be running 10,000. And we don't need that degree of precision, at least at first. So I'm going to set it to 1,000. You don't click Start Simulation. You go into Risk Optimizer and you click Start there. And it'll take a minute to get started. Now it's running. There's a little button down here at the bottom left, which if you pull that up, allows you to watch what's going on. So it has several tabs. The progress tab is showing what the mean of the profits look like as it tries different values. And it shows for the last 50 and all trials overall. So you can see it found something a little bit better. Actually, it's done. It found a solution. Because I only had to try 10 values for each. If you look at the summary tab, it'll show you what the best solution was, what it started out with, what the last one was. And the best one actually was to have $100 for the peak load price and $40 for the off-peak load price. You can get a log of all the things it tried and what happened. If you click OK here, it'll paste it into the spreadsheet. But I only allowed the peak load price to go to 100, and we obviously need to allow it to go higher because maybe higher is even better. So let's go back into that model definition. It looks to me like we don't need to set minimum as low as 50. Let me set it at 90 just in case for some reason that 100 was not really the best, that something close to that was better. But let's go up to 150. And again, I'll leave that at 0 to 50. Actually, you don't need to leave it at 0 here. Let's go from 30 to 50. And let's decrease that step size to 2. And let's run that again now. That ran so quickly, I forgot to look at something here, but we'll look at it this time, that you want to look at in terms of watching the progress. The log is a useful thing to look at because what you want to see is whether the solution is by far the best one, or whether there are several that might be close to it. So if you look at the log here, what it's trying, so well, still the best one was the first one, but you want to, okay, it's found its best value, keeping the original one, so at 140. If you look at the log here, instead of looking at all trials, let's look at the progress steps. Well, actually, I guess the first one was the best, so I guess we should look at this. So what you might want to look at here is these two price cells and see, since, well, I did let it do steps of 2 here for the off-peak price, but for the peak price, I had steps of 5. So if we look at the best one is at 100, what happens, the 140 was the best, what happens if we're slightly different, like 105? 105 and 34 came out with a mean of 7,400 rather than 13,000. Here's one that's close. The 9th one, instead of 13,000, was 12,300, with this at 95 and that at 40. So that gives you a good feel that, in fact, 195 is sort of the right region, and this one's the right region at about 40. Then I would probably run it again where we specify only from 90 to 105 in steps of 1, and maybe lower the steps of this, go from 40 to 50 in steps of 1, just to get more exact. Let's see if there are any other solutions that are kind of close. All right, here are 2 that one's almost 13,000, 95 and 38. It's in the same vicinity. Especially if you have a big problem and if you run 5 minutes and it stops and it hasn't found a solution yet, what you want to look at and see is, are the top few solutions, they're not the solution, but the top few are close to each other, you will pretty much know the range that you want to look at in the next iteration of running this. If the solutions are very far apart, like you've got 2 that are almost the same output, same profit, but the prices are very different, then you know that you haven't come close to a solution yet. You need to run it longer. And you always, when it stops and hasn't found a solution, it always gives you a chance to do it longer if you want to. Here it was able to find a solution from the steps that I gave it. There was nothing better. Let me see if there's anything else that stands. Here's another one. 12,600, 142. Again, it's in the same range, so pretty sure we're in the right range. This one's almost 13,000, 95 and 36. So you get the idea. You might want to look at prices below 40, as well, a little finer, going from 35 to 45, and this one from maybe 90 to 100. That would probably be my next step, to do it that way. But I'll keep this solution for now, which is setting this at 100 and this one at 40, and the profits. So now what you want to do is you want to, with that pasted in, now you want to run a complete simulation. So I'll change it back to 10,000. I'll start the simulation. This is what the profits look like. And notice it came out to 13. The mean, what's showing here is the last simulation, not the mean. The mean is 13,112. That's the best mean that you can get. Now, the way that optimization works here is not just to find a solution to this problem, but to get this solution, I almost prefer just doing some data tables and seeing how the prices translate to profits. You get a better feel for the solution as opposed to optimization, which is kind of a black box. Throw it in, let the computer tell you what the solution is. But the optimization becomes a lot more interesting if you were then to look at this, let's say, and say, you know, that it's too much uncertainty about this profits. You see a 90% confidence interval goes from 9,500 to 16,000. The standard deviation here is about 2,000. Suppose you wanted to reduce the standard deviation and you didn't want it to be more than 1,500. What you could do is you could go back here to the risk optimizer and you could add a constraint here. You want to constrain the standard deviation of the profit. So it's this cell, profits. In this case, it's a simulation statistic that you want to constrain. You want to constrain its standard deviation to be less than or equal to 1,500. So there's a hard constraint. There are some, you have to read about all the options here. There are options of making it a soft constraint so that you can, better than that would actually do to run an efficient frontier, which is described in the book. And you can see that you can actually say, let's see how, as the standard deviation varies, how does the profit vary? Sort of a risk return trade-off that you can actually map out with an efficient frontier. But just to see how it works with a constraint in it is, let's leave that, change this back to 1,000 and try running this, because you'll see as the progress goes on that things change a bit, because now it's going to start with the solution that it had found before, but that's not feasible because the standard deviation is not less than 1,500. So it's going to reject that as an ineligible solution since it's not feasible. Okay, so it's running now. Let's look at the progress. So it actually did find something. Setting the peak price at 110 and the off-peak price at 46 gave a feasible solution, and so far that's the best one. And it went through all the values again. I had pretty big steps there, so I'm not very close to a precise solution. Let's see actually. The best solution is the 44th. see if I can. Notice all these negative values. Trying to reduce the uncertainty that much is causing most of the values that I gave it to try to have negative profits. It could be this one. No, not quite. 115 and 46. So there is something better than that. Notice the standard deviation, though, is feasible, 1370, which is less than 1500. So is the next one, but the next one has a mean profit of negative 2700. So that's clearly not what we want. Here we get almost 13,000 of profits, but notice the standard deviation is too high, so there's too much risk. Now this one's looking more promising. That's almost 11,000 of profit, and it is less than 1,500 standard deviation. That was 110 and 46, which I believe was the solution. Yeah. So again, what you want to look at, though, is now you want to see what comes close to it. Do we have another feasible solution close to 11,000, but with the standard deviation that's like close to this value of 10,793 with the standard deviation? Well, notice this one, 989 for the standard deviation is 8256. This is why you might want to do an efficient frontier, because you really would get more information. Like you could reduce the variability by 50% here, only giving up about $2,500 of profit. So it might be worth that trade-off. That's really what you're looking at exploring, is that trade-off. But that is $2,500 of expected profit more. All these NAs mean these are not feasible solutions. The feasible solutions, many of them have negative profits, which is not very appealing. And others have, here's the output mean, they do have positive profits, but not nearly as high as our best solution. So we did find a solution here, although again, to be more precise, you'd want to then, you'd want to narrow that range and do smaller steps at least to get closer. Again, what you would do here, it's now pasted in that solution, is you'd want to run a simulation with more iterations, do the 10,000. Verify that in fact the standard deviation is still less than 1,500, because we only ran 1,000 simulations to get that solution. Now you run 10,000. If you were close to the border, you might find that you're not under 1,500, but we are well under it, 1,403. So that's a constrained optimization problem. It's the interesting thing is, for constraints, you can put constraints on on decision variables, like saying they can't be negative, or that the total, the price difference. I mean, I could see there might be a political constraint that you can't charge more than twice as much in the peak hour as the off-peak hour, and our solution doesn't satisfy that because we have it over twice as high in this solution. So then we could add that constraint in on decision variables. You can constrain intermediate calculations. You can constrain the very variable you're trying to maximize. That's a very typical thing to do. Say, I want to maximize this, but I also want to limit its risk, measured by, let's say, standard deviation, or you could say a percentile. You could say, I want the fifth percentile, the lowest 5% of the simulations to result in positive profits. That could be another kind of constraint to put in. So there's a lot of flexibility on how you can set up your problem. In any case, the basic procedure, though, is just to not plan on running it once, plan on running it several times. Start with a wide range and big steps. Look at the solution. If it's at near the edge, or there are solutions almost as good that are very close to the edges, you might want to enlarge the range. Otherwise, if it's somewhere in the ranges that you gave it, like in this case, 90 to 150, we could get more exact now. It came out at 110. We can go ahead and say, let's narrow it to 100 to 125 in steps of 1. And keep doing this several times, narrowing the range, decreasing the step size. And if you actually need an absolute continuous solution to the problem, that's when you set the value on any, so that it can be, fractions of a dollar. But it's going to take a long time to run because you're letting it try an infinite number of solutions. If the problem is simple enough, it may not take that long to run, just because it's doing kind of an intelligent procedure of finding the solution. It's randomly jumping around to imitate sort of the way biology works, so mutations, saying, this looks like about the right range, but let me jump over here and see if I get something better. And it'll do that enough times that it can narrow in on a solution without trying every conceivable value. If it's tried enough in the region of different values, it doesn't have to go back there. If prices for off-peak hours of $20 were not giving good solutions, it won't try too many down in that range. So it's somewhat smart, but mainly the speed of the computer to try a lot of different values is what gives it its ability to find a solution in a reasonable amount of time. Anyway, that's how Risk Optimizer works. You have examples in the book where you can try this out. I'm not a big fan of optimization myself, but when you really want to analyze the risk-return trade-offs, this becomes a very effective way to do that.